Hi and welcome everyone. By now you have learned how to solve second order linear homogeneous differential equations with constant coefficients. In this video I will show you some situations where you might encounter these type of differential equations in real life. We will mainly discuss the mass spring systems, but also touch upon an electrical circuit which features this type of differential equation. Suppose that we have a mass that is attached to a spring. We measure the location of the mass by considering the vertical displacement, which we will call y, with respect to the equilibrium position. Other quantities that will play an important role are the vertical velocity and the vertical acceleration, which are given as the first and second derivatives of y respectively. The physical law that will bind everything together is, what else? Newton's second law of motion, which states that the total force is mass times acceleration. Of course, the acceleration is given by y double prime here. So we find that the total force equals m times y double prime. So which forces are in play here? Well, if you ask this question in class, usually the first answer that comes up is gravity. But gravity is already taken care of, since gravity determines what the equilibrium position is, and we measure the displacement with respect to equilibrium. So gravity does not play a role here. Instead, the important forces at play here are the spring force, which is given by constant times the displacement, friction, which for low speeds can be modeled as a constant times the velocity, and possible external forces. Rewriting this equation brings us into the form that we recognize as a second order linear differential equation with constant coefficients. From now on we assume that there is no external force, so we set the external force equal to 0. This means that the differential equation we obtained is homogeneous, so we know how to solve it. We will fix the values of the mass and the spring constant and take a closer look at what the influence is of the damping coefficient on the shape of the solution. We provide some initial conditions which allow us to sketch the solutions we obtain. In each case we assume that the mass is equal to 1 and that the spring constant is equal to 25. We will take a look at 3 different values of the friction coefficient, which will turn out to correspond to 3 qualitatively different cases. Let's first consider the case where the friction coefficient is very high. Since this equation is a second order homogeneous linear differential equation with constant coefficients, we solve this equation by making the ansatz, educated guess, that y as a function of t is e to the power lambda t. Plugging this ansatz into the equation and finding the roots of the characteristic equation, we obtain 2 real roots, being -1 and -25. We know that this means that the solution of this differential equation is a linear combination of the 2 exponential functions. And by plugging in the initial conditions, we find the exact shape. Notice that when t becomes very large, e to the power minus t is way larger than the other exponential function. So this solution goes to 0 as fast as e to the power minus t, which in this context is not very fast. That is why we call this the overdamped case. The damping coefficient is so large that if you stretch out the spring, it will slowly move back to equilibrium. You can imagine this happening when you place the spring in a medium with a very high friction coefficient, such as water or even something like honey. Let's now take a look at the second case. Again, it's a second order linear homogeneous differential equation with constant coefficients, so we make the same educated guess for the shape of the solution. In this case, we only find 1 root of the characteristic equation, which is -5. Now we have a double root, so we know that the solution will be the linear combination of the exponential function and t times the exponential function. Plugging in the initial values gives us this solution. Notice that this solution goes to 0 much quicker than the previous example because it goes as fast as t times e to the power minus 5t, while the previous one goes as fast as e to the power minus t, which decreases a lot slower. This case forms the transition case between the previous case and the upcoming one, and that is why we will call it the critical damping case. Finally, let's take a look at the lowest friction coefficient. Again, we try y is e to the power lambda t, and we find two complex roots. This means that the solution will be a linear combination of an exponential times a cosine and an exponential times a sine. And, again, we can find the coefficients by means of the initial conditions. Because of the presence of a sine and a cosine, the solution will oscillate and it will go to zero because of the exponential damping factor. Notice that the solution goes to zero slower than the critically damped case. We call this case the underdamped case. You can imagine this case occurring when the friction coefficient of the medium is very low. For instance, when the spring is moving in air. Then the spring will start oscillating with a decreasing amplitude because of the friction. As you can see, the critically damped case is really the transition between the overdamped and the underdamped case. In a picture, the solutions look as follows. You can clearly see the behavior we just described. The overdamped case does not even go through equilibrium, the critically damped case goes to zero the fastest, and the underdamped case oscillates the most. It depends on the application which of these three cases you want for your mass spring system. As a final application, we will also consider something that initially looks very different, but in fact has very similar properties to the mass spring system. This is the so-called source-free RLC electrical circuit. What you see is that a resistor with resistance R, an inductor with inductance L, and a capacitor with capacitance C are placed in series without a voltage or current source. We're interested in the current I that goes around this circuit. By means of the Kirchhoff laws and the physical properties of these three circuit elements, we can derive a second-order differential equation for the current, which you see over here. Notice that this second-order differential equation is linear, homogeneous, and has constant coefficients. By plugging in some numbers, we can arrive at the exact same equations as we saw before, which means that the solutions also look the same. Hence, the terminology overdamped, critically damped, and underdamped is used in the context of electrical circuits as well, and you will encounter it in books on this subject. That's all for now. I hope you learned something and see you in class.